Hello. We will give a talk on why cities should expand their own environmental monitoring with additional data sources. This presentation will be given by myself, Henrik, and Nuria, and Gabriela Sousa Santos and Amir Hussain is also part of our team. But this is presented here are results from the whole CoMobility team. I will first go through some background information on air pollution and then go into modeling before Nuria will talk about sensors and then finally some summary and take-home messages. So why is air quality important? Air quality compounds regulated by air quality have the common denominator that they are harmful for human life. We get it into our body through the respiratory system, and there are many symptoms. Most of them are long-term increased chance of various diseases, mainly in the lung and respiratory system, but also in other organs. The components we will be focusing on today is NO2 and particulate matter, which is any solid or liquid material suspended in the air. We breathe them in and they attach to the body and then they don't leave. And all of these compounds have a long history of well-documented detrimental health effects. So when we get exposed to poor air quality, we breathe it in. It goes into our system. We can get increased chance of respiratory diseases. It also affects the heart and other neurological effects. This in turn increases morbidity and mortality, so we get more sick and it increases the chances of premature death, which has a cost associated with it in terms of loss of productivity and health expenditures. So in many cases, dealing with poor air quality can be a very economic, viable option to improve, also in economic terms. Air pollution has been regulated through history. It's not a recent thing. Even in antique Rome, there were regulations where citizens were bound to water the roads around their houses to prevent dust from escaping from the road, and then improving air quality in the cities. In the Middle Ages, King Edward was probably asthmatic, and he banned the use of coal when he was in town in London. More recently, the Industrial Revolution led to heavy coal-based industries in many European cities. And it gradually deteriorated the air of the cities, all the way to the conditions we recognize from Dickens' London, where this gray haze was hanging over almost any city. This led to the first modern laws in the 1980s, where there came regulations for heavy industry, forcing them gradually out of cities into other areas. In the 1952, the Great Smog of London happened. Almost 5,000 people died in a few days, which were caused from coal firing in residential heating. This has led to several laws following in also not necessarily in England, but around the world, also on residential heating. And as another modern example, we have had leaded petrol for many years, which was banned in most countries by 1997. And now, finally, in 2021, a global ban was achieved for leading petrol. Air quality in Poland is problematic at times. Sporadic episodes, especially in winter with heavy air pollution, are observed through the monitoring networks, and nearly 1 in 10 deaths, or more than 1 in 10 deaths in the EU is in Poland. The main sources of emissions varies with components. For NOx, which is a gas composed of NO2 and NO, the main source is road traffic and transport. And in Poland, there is an old car park and a very high car usage. For particles, residential heating is the dominant source. There are very many small sources that contribute across the country, and also heavy industry and power production contribute significantly to both of these. But as we can see on the bottom left, Poland has commitments to reduce NOx, PM2.5, and also SO2, for example, which it has set some years ago, and are gradually reducing its emissions, even overachieving the aims they have set. So on the NOx front, which is mainly associated with car traffic, very mild targets for reduction were set, and the reduction isn't as deep as for other components. So in a city, to know what is in the air, you need to measure the air somehow. We have an international network of reference monitoring stations. Here shown in the Greater Warsaw area, there are 9 stations measuring various components, and they can tell us something of what is in the air where they measure. Of course, the location of these stations are important because they will be dominated by the local sources. These stations are expensive, and it's hard to cover an entire city with these kind of measurements, because air pollution is highly spatial and temporal variable. It varies a lot. They have a short atmospheric lifetime generally, and concentrations can vary significantly across time and space. So the reference monitoring stations aren't necessarily enough to understand what is going on in the city and how to improve air quality. And now we have looked at emissions and concentration, but if you want to look at what we really care about, which is the exposure, which is what leads to diseases, we need to know what the concentrations are where people live and move. So there are several ways of filling these gaps in between the reference stations. We have options of local sensors, which Nuria will talk more on later. And we have the option of doing numerical modeling. Both of these methods are dependent on having reference stations to anchor the results from these tools. And of course, they are supplementary, so you can use all of it together to achieve the best results. In numerical modeling is a multi-model process. You need a lot of input data, so it's quite costly to set up. You need metrology to capture the movement of air. You need to know what kind of activity goes on in the city, what sort of emissions is associated with this activity, where it is, when it happens. And then you can do a dispersion model, which despite being very heavy and costly to set up and validate, It gives very rich information in terms of details, uh, uh, and gives the opportunity to make scenarios. You can make alternate realities where you implement some changes and then you evaluate the results. And this part I will talk about now. In CoMobility, we set up this environmental modeling system all the way from using MTOD, the traffic model, to model all traffic in the greater Warsaw area. In addition, we had the field service, which I believe have been described in detail earlier in this meeting, with questionnaires. We used a traffic emission model that was adapted to Poland using the Warsaw car fleet and the Warsaw traffic and congestion details. Our focus area, and then finally we made a dispersion, numerical dispersion model, which is called episode, where we modeled air concentration for all the year of 2019. Our main focus area was 3 schools, and we targeted also then the parents driving their kids to schools, which we had covered in these questionnaires and surveys. These 3 schools are located in 3 different spots, locations in Warsaw. One is the Kruszków-Giego, which is located in central Warsaw, in the more lightly dense populated area, Trocka, and Kajki, located in the suburban area. From all of these schools, we modeled traffic on the roads near them, specifically. And we were more interested in the pickup zones around each schools, which are denoted by a red dot in the images. Then several different interventions were planned and carried out, which I will now show something about. In our traffic model, we can't model everything, but we can model changes in traffic and driving behavior. And our first scenario was that we assumed that no parents drive their kids to school. Kids would find other means to get to school, and we removed all the traffic associated with bringing and picking up kids to school. The second scenario, we reduced accessibility of the schools by cars. We removed parts of the road, so it got harder so that we lowered the capacity of these roads. And in the third scenario, we altogether blocked the roads near the school entrance to see what effect was coming from the very, very local specific area. So here are the annual, up on the right is the annual average concentration level at the school entrances in dark blue. The pickup and delivery point of time is actually significantly higher concentrations. This is due to the fact that this happens during the rush hours, where traffic is heavy and there are elevated concentrations. So when we blocked the road near the entrance, we took away all traffic on these roads, and in the points of the pickup zone, NOx concentrations predictably dropped by about 12 to 24%. So that was a positive thing. But of course, blocking off a whole road is a large inconvenience and not a realistic way of dealing with this. And what we actually saw was that emissions in a larger area was actually increased due to longer driving distances and the congestions that were created. So people had to drive around the schools and find other routes, and not necessarily traffic connected to the schools, but we made a lot. So overall emissions went up. In the reduced accessibility scenario, where we use some traffic calming methods, we got similar results, but much weaker. 2 to 5% NOx reduction in the pickup zone. So also reducing the access on the road is an inconvenience. And again, we saw the same result, that as a result of the reduced accessibility, emissions just moved to a different area. And we got increased driving distances and more congestion. So while this scenario 2 created a local success around the school, as you can see from the map here, red denotes an increase and blue a decrease in concentration. So right around the school, you get a decrease. But if you include a larger area, as is very apparent in Kaiki, where you can see that traffic shifted from the road that was blocked to the next road. And so when we look at the larger area, actually emissions and concentrations increased. The final scenario, where we took out all parents driving. So you just take out some traffic and you would expect to get a good result overall. However, we noticed that we achieved very, very little in the actual school areas when we reduced when we took out all the parents driving their kids to school. And the reason for this is that when you remove vehicles from one area, over time, people will realize that this is an advantageous route and will choose this route instead of their previous one. And so when we look at the larger picture, when we take out parental driving, we had a reduction in emissions, but the consequences around the schools were minimal. And even in the case of Trocca, it had increased concentrations due to some different routing options. Now, one effect that we are working on incorporating into the emissions now is that a passing vehicle is very different than a school pickup. And the reason for this is that the vehicle that is dropping off or picking up a kid, it has much longer time on the road near the school. It may have to cruise for parking, finding a place to stop. When it has stopped, starting the engine again produces extra emissions. Also, the act of parking and maneuvering have very high per time emissions associated with it, due to the acceleration and deceleration. And of course, if you don't turn the engine off, you will stand there idling. And all of these maneuvering can create congestion for other vehicles, increasing also their time around the school. Here is an example of a vehicle in the red dotted line, of picking up a kid at the Trocca. A passing car spends about 47 seconds in the vicinity of the school. This particular car picking up a kid drove in, had to turn around to the other direction, go back a bit, then spend some time parking into a parking slot, then didn't turn the engine off, was idling for about 1.5 minutes before the kid got in, then had to get out of the parking area again and continued on. And as a result, it spent, instead of 44 seconds, it spent nearly 5 minutes in the area, which most people would say is not unusual for a pickup time. The result of this, however, is that emissions from this particular pickup on the road near the school is almost 30 times larger than a car parking, just driving past the school. So with the numbers and details from the field survey that was done outside the schools, and also we want to incorporate this effect into our simulations. And we're also working to assess the actual interventions that were done. The final part that is also ongoing is to scale this up to all schools of Warsaw. So as a summary, episode was used to assess air quality for all of Warsaw in 2019. This simulation made the foundation for detailed studies of air quality in Warsaw, and we're still working here with more to come. We are modeling new combined scenarios, which should give better results. And the pickup zones around the schools are especially sensitive areas because here children move in and around traffic, and they are, in most people's lives, it's the time of the day they are exposed to the worst air quality. These scenarios we have modeled gives insight not just for the air quality of the pickup zones, but also how to more efficiently improve the air quality in that area and have targeted measures and interventions that have an actual effect, which without being too much of an inconvenience. And finally, I think I will then pass the words to Nuria.
Thanks, thanks, Henrik. So as Henrik was saying, like air pollution has varies very much from street to street, right? And this we are not able to capture it when using traditional air quality monitoring. So what I'm going to present is these new technologies that are now available to monitor pollution, the so-called low-cost sensors. So if we compare to conventional methods, the air quality reference stations, one can see that low-cost sensors are not as accurate as those, but on the other hand, they are easier to deploy, they are smaller, and in most of the cases, they require less maintenance, what always lowers the cost in that sense and allows us to have dense sensors networks, as the one, for example, is already existing in some areas of Poland. Next slide, please. Can you, yeah. So there is an evolving landscape in the use of technology. There is, like, if one goes to the market, we see like an overwhelming number of manufacturers providing sensors, always with big promises of accuracy and reliability, but this is also like not always the case, and it's still very important to one have also this quality control of the data, this quality assurance, assessing how the sensors perform. However, once as this is an evolving landscape, it's like the technology is fastly evolving and developing, and we can see, like, if we compare with 10 years ago, we can see that the market and the sensors are more and more accurate and get more into the demands of municipalities and scientists, so that we can start using them more and more for more applications. Yes. So what I think, like Henrik said this very well, like both modeling and also the use of sensors is still requires to have the conventional monitoring, to have those reference stations in place. And for the sensors, this is this making sense of the data. We have these dense sensors of networks. Then we need to apply this quality assurance, quality control, and calibrations. And for that, we still rely on the reference stations. Here in the picture, you see an example of Kristiansand as a city in the south of Norway, where we have two monitoring stations there, having particulate matter and nitrogen dioxide. And then with the use of low-cost sensors, we could expand this to have over 40 new measurements in the city, what allow us to have data in places that was not available before. And also another strength how we can use sensor data is also in combination with air quality models. In that sense, like as Henrik was saying, having an air quality model that properly gives you outcomes, it depends a lot of the inputs and the data quality. You need to have accurate emissions, accurate meteorology, etc. And this is not always possible in all cities. So then, like these combinations of sensors plus models can help also to improve and create these real-time or near real-time air quality maps or average maps on air pollution. So here in this picture, what we could see is like that also sensors allow us to improve or strengthen the use of air quality models. So this is another use of the low-cost sensors. Yeah, next slide, please. As I mentioned before, like quality assurance and quality control and calibration is very important. I will not draw into the data here, but it's something like, for example, at NILU, we have developed the NILU sensor database where we do perform these calibrations in order to assure that the data that as it comes from the provider is quality controlled, and then it can be used by authorities or the municipalities or even the citizens that can use this for their own information. Next slide, please. Also, like, I don't want to draw into that, but for example, like one of the clear things that also were very important for this project is that the PM 2.5, the particulate matter, it's affected. The sensor is affected very much by relative humidity. Thus, a correction of this data, it's important. Otherwise, we might give values to municipalities or to residents that are not good. Next slide. Yes. So I'm going now to give you some examples of how we are using these low-cost sensors at the NILU. This is an example from Green Heat. This is another project NILU is collaborating about biomass heating in Legionowo, nearby Warsaw. And here, just like I want to recall, like this is a small area. What you can see in the circles, in the orange circles, is the concentrations from sensors deployed in the area, and the pink square is the reference station they had there. So you can see that even in a small area, we have large variations because with burning, biomass burning in the area, it changes a lot. And actually, when we talk then with the municipality and with the experts in the locations, they already told us that the larger concentrations actually correspond to areas where they have been receiving some complaints about the smell and also about the possibility of their burning trash. Next slide, please. This is also how we are using it in Kristiansand. This is the same network I was showing you before. And here you can see a bit larger on the right part of the screen, this combination of observations from the low-cost sensors with the model. And here what it was very clear in this particular case was as a neighborhood that was in a valley where they were using wood burning. The model was underestimating, probably because of the very local meteorology in the area, and with the help of the sensors, then we could have this very broad picture of the temporal and spatial variability of the concentrations. Next slide, please. I've been talking so far about static monitoring. This is like sensors you can mount on the lamppost, on houses, etc. But there is also the possibility with the sensors of having this mobile monitoring. This is a pilot we conducted also in Kristiansand, and here you can see a rack of sensors that were mounted in this case for testing, but you can mount one of those in the bikes. We gave 10 of them to citizens in Kristiansand, and it was amazing in a period of a couple of weeks. So like the large amount of data that we were able to collect. Plus, this also gave the citizen or the person, the participant carrying the sensor, the opportunity to check their exposure and also increase their understanding on the causes and effects of air pollution. Next slide. And how did we work in the CoMobility? In the CoMobility, we installed air quality sensors in the schools. Actually, in each school, we installed 2 air quality sensors, one in an area close to the traffic and one in the backyard or nearby the backyard. And we also complemented the data from the air quality with a sensor monitoring noise that was installed also in the area nearby the traffic. Next slide, please. This is just an example of the data that we were collecting from October 2021 to February, March 2023 in the three schools. And here, we have the sensors. In blue is the sensor that was located to the backyard. In orange is the sensor next to traffic, and in yellow is the data from the reference station that is nearest to the school. And what we can see here is that all of them, the sensors and the station for PM 2.5, they have the same pattern. That's very good. That's a good sign that the sensors, after this quality control and calibration, they work and can offer us data. And but also we see also differences, what is normal, because as we said, there is variations, right? It's not the same a school in the center that the school outside of the center of the city. Next slide, please. Here, what we show is the diurnal variability that we have for the particulate matter. On the top figure, we have the three schools. That was for all the data, all the period from October to 2021 to March 2023. And then we also have only for the periods on the figure below, the periods on during winter. And what we see here also is during, especially concentrations during the winter are especially larger during the evenings, what usually corresponds to the use of biomass burning. And also we observe in general higher concentrations during the winter than during summer or during spring. also, like if we look at the noise nearby the schools, this is still like needs more analysis, but we can see that outside the school, not inside the classroom, but outside the school, like the levels are quite high. So this type of sensors allow us, to this going in deep inside of what's happening in our schools. So yeah, next. So yeah, then floor to Henrik, or maybe it's just summarize a little bit with the sensors. They offer us this possibility of having detailed measurements in areas that we really care about, like the schools, hospitals, or hotspots in the city. We can get this really near real-time monitoring and the data for most of the pollutants like PM2.5 can be used to give us an insight on how the levels are, even if they are not as accurate as reference stations. And when we take the power of the three monitoring, right? Like we've got the modeling, there's sensors and the reference stations, then we can really enhance the knowledge about the temporal and spatial distribution we have of air quality. And Henrik, please. Thank you.
Yes. No, like Nuria said, that often the sum is larger than the parts. To add everything together often gives the best information. And I would stress that this reference air quality stations is a requirement to do air quality modeling with accuracy, because both the modeling and the local sensors need them to calibrate against, and they found the anchoring point for any work. But this work gives us wide information, and they also allow us to individually examine what we want to do and how to achieve it, and we can do that in a numerical model, for example, without actually doing it in physical real life, and we can discover mistakes or maybe also different and better methods to do it by just testing various methods. And from CoMobility especially, it's very hard to get less pollution without lessening the overall driving. And to achieve that without becoming unpopular, it's important that citizens are engaged, and they are willing participants in changing their mobility choice. And the best way to do that is by making less polluting mobility choices more convenient. So I think that was it.
I have a question, can I?
Yes.
Maybe I'll switch in Polish. Is it okay? Is there a translation to English so that you...
Yes.
Będzie prościej. Pytania
I can
do...
provide the translation.
Po pierwsze, część badania, czy wariant bez rodziców podwożonych dzieci do szkoły było robione jakoś we współpracy z rodzicami, czy po prostu w dni bez nauki szkolnej? To jest pierwsze pytanie. A po drugie pytanie, czy ja dobrze zrozumiałem, że wyszło Wam z badań, że zamknięcie fragmentu ulicy przed szkołą pogarsza jakość powietrza na alternatywnych trasach? Dzięki.
So I translate the questions. First one concerns whether we observed air quality with our sensors during school days or the entire week. And the other question is it correct that Thomas understood that we had worsening of air quality in the neighboring roads after closing the road by the school? So I think these are respectively questions to Nuria and Henrik.
Okay. Yeah, so oh my God, kind of forgot the question now.
I can answer the second part first about the worsening of surrounding roads. That is correct. When we just closed the road, the total emissions and total traffic, it went up. And as a result, if you look at a wider area, the traffic basically just went around the roads, and total emissions went up.
And the first question was, how did you achieve the parents not to drive their children to school? I mean, was that only a measurement on a school-free day without drop-off traffic, or was it somehow in cooperation with parents or with school?
This was only done in the traffic model. So the trip the trips generated by parents driving their kids to school was basically, we removed it from the traffic model, and then we evaluated the results of the model. So this was not an actual implemented thing that was done. We merely wanted to see what was the effect if we achieved this.
I see. Thank you very much. Very interesting presentation. Thank you, guys.
Thank you.
Yeah, and now I remember the question, sorry. Yes, so if we didn't put the figures, but if we, for example, see the air quality during work days or weekends, right, like when the school is closed, then we can see differences in air quality. But as Henrik was explaining, we cannot say this is because of the parents driving, right? Like, this is difficult to say because in general during the weekends there is less traffic. So we also see this, for example, like that the noise levels are lower during the weekends and working days.
Skoro nie ma więcej pytań, ja chciałbym bardzo podziękować Nuri i Henrikowi za tą prezentację. Thank you, Nuria and Henrik, for your presentation. Panie Konradzie, również dziękuję za wsparcie nas tutaj w tłumaczeniu. Wyszło bardzo, bardzo fajnie.